So now coming back to the part 2 of this lecture. So we'll come back to this question about what is the line element, what are the transformations which leave this line element invariant. So this is what we'll start off with. So I'll define some notation. I won't go into the full details, but meaning all the details, but let's just see how far we can go. So let's start with the ds square in one frame of reference, which I'll call it as theta 1. In this frame there is a line element called ds square. This is nothing but dx mu. So in another frame theta 2 there is a line element ds prime square. This is given by some dx prime mu. Now we want to ask the question, what is the one which is relates these two? So the most general way we can write any four-vector transformation in this particular is in this particular fashion. So O1 to O1 to O2 is given by some transformation, Lorenz transformation, x mu nu is equal to lambda mu nu dx mu prime. Now we know that dx mu should be equivalent to dx prime mu dx prime mu. This gives you the condition, this leads to the condition that lambda mu nu, if you apply this one carefully, lambda mu rho is equal to delta nu rho, where lambda mu nu is the something called the Lorenz transformation. So matrix which is called the Lorenz transformation. So what we have seen is that so delta mu nu is nothing but a Kronecker delta. Such that when delta mu nu is equal to 1, when nu is equal to rho and is equal to 0 when nu not equal to rho is not equal to. So if mu nu is a Lorenz transformation, and then rho mu would be it's the inverse Lorenz transformations. The inverse Lorenz transformation. Now this lambda, if you count the number of parameters, if you do it, it's a symmetric matrix. Say symmetric matrix, and it turns out it can be described in terms of 6 parameters, because it's a symmetric real matrix. It will have how many elements it will have. So just check why you should have 6 elements, because you have one more condition of this particular type essentially. It is a specific kind of orthogonal matrix, a specific type of orthogonal matrix Orthogonal matrix means O transpose is equal to 1. In fact, it forms a group, as we will see later, which is called SO31. All the Lorenz transformations form the group SO31. We will come to what is this definition of a group in a SO31. We will come to it in a second actually. So what we have seen is that a Lorenz transformation can be defined in terms of 6 parameters, and there is something called the inverse Lorenz transformation, and all this comes out purely from this definition of meaning that the line element should be the same in every frame of reference. So the line element is same in every frame of reference is the only definition which we have. Okay, that is the only element we use, and from there we get all these conditions which we have described so far. Okay, now we'll see some. Now this is sort of maybe up to this particular point may not be completely familiar with many of the people. Let's look at the familiar Lorenz transformations which many of you must have encountered in your classes. So if we have parallel Lorenz transformations, so you have vector a reference frame O1 and another reference frame O2 which is moving parallelly with a velocity now very close to C. Okay, so let's just take x in this particular direction, it's only moving in x, and the other direction I take it to be time. So unlike x, y, z in the previous case, we had taken it as x and t in this particular case. So this distinction you should keep in mind. The Lorenz transformations are given as follows. X prime is equal to gamma x minus vt, y prime is equal to y, z prime is equal to z, t prime is equal to gamma into t minus vx by c square. This is your familiar Lorenz transformations which you have studied it in your, some of you in your undergrad or some other courses actually. Now what is the definition of gamma? Gamma is 1 by square root of 1 minus v square by c square. So this entire thing can be re-expressed, okay, in this particular format. Okay, so re-expressing so let's just take y prime identity transformations, so I don't really care about them. So let's just write x and t. So x prime ct prime is equal to gamma into 1 minus beta minus beta 1 x ct, where beta is nothing but v by c. So, okay, so this again I re-express it in terms of x prime ct prime is equal to cos psi minus sine hyperbolic psi minus sine hyperbolic psi cos hyperbolic psi into x ct, where psi is defined by the tan hyperbolic psi is nothing but your beta, is nothing but a v by c. So, psi is something called the rapidity. So, when beta, which is nothing but v by c, which has a range from non-relativistic case to all the way up to b. Okay, so beta can belong to only this interval which is when v is equal to c. In that limit, whereas the rapidity range minus infinity to plus infinity, because the way it is defined essentially. So, in the limit when the beta becomes 1 or the v by c is equal to 1, okay, what happens to psi? Psi becomes positive infinity, so infinitely rapid. So, what we have is other trigonometric variables you can define. Sin psi is equal to gamma beta, cos psi is equal to gamma, and so now we can check that you get back your result essentially. Now, what is the advantage of writing it in rapidities? Now you know that you can the reason why we introduced rapidities is because we can understand a few things very nicely in this particular fashion. If you write it in terms of rapidities, rapidities add up for successive Lorenz transformations. So, this is the advantage of defining things in terms of rapidities. Okay. Okay. So, this is the advantage of writing in terms of rapidities, the Lorenz transformation. So, now we have a series of Lorenz transformations, say for example O1 going to O2 going to O3. So, the final Lorenz, so this one has a rapidity, say going to this one is a rapidity parallel Lorenz transformation psi 1, and this one has a rapidity from theta 2 to theta 3 is xi 3. So what you have from theta 1 to theta 3 would just become xi 1 plus xi 2. So if this Lorentz transformation is given by xi 1 and from theta 2 to theta 3 is given by xi 2, okay, the total Lorentz transformation from 1 to 3 is given by xi 1 plus xi 2. So you will have things like cos xi 1 plus xi 2 sin h hyperbolic xi 1 plus xi 2 cos xi 1 plus xi 2 and so on. When I put a star, it means the same thing which comes here essentially. Okay, I can write it again anyway. Sine hyperbolic xi 1 plus xi 2. This is a Lorentz transformation which is from theta 1 to theta 3. Okay, so the rapidities just add up. So now you can ask the question. So we have one set of rapidities, so in the x direction. So similarly, you can have rapidities in y direction. You have rapidities for z directions. So all of them form a group. So for example, what does a group contain? A group contains a set of operators satisfying the following properties. So it's closure means, so if there is a group G, so if there is an element A1, so A1 star A2 also belongs to G. So for A1 A2 belonging to G, A1 star A2 also belongs to G. The second is associativity. If there are elements A1, A2, A3 belonging to G, then here, sorry, I didn't mention, star is the group multiplication. So in this particular case, this is just like a matrix multiplication. So associativity means if you have A1 star A2 star A3, that should be equivalent to A1 star A2 star A3. Then 3, identity. That means there exists an element E belongs to G such that A1 star E is equal to E star A1 is equal to A1 is equal to belongs to G. Okay, A1 star E is equal to E star. E is an element of the identity, element of the group G. I is the identity. Then there is something called the inverse, such that for every A, okay, for every A belonging to G, there exists A1 inverse such that A1 star A1 inverse belongs to G. And it's not just that, A1 star A inverse is equal to E, which again belongs to Z. Here belongs to G such that. So if this set of all transform, this set of operators which belongs to Z, so if there is a set of G, A1 and AN, this could be continuous, okay, discrete, and so on. So this is a group which is continuous group in the present cases. If this continuous group, we'll see it, which satisfies these 4 properties, which are essentially closure, associativity, identity, and inverse, then such a set is called a group. Okay, such a set is called a group. So this set, it can be continuous group or a discrete group. What do I mean by continuous group? Continuous means these A1 and A2 and AN are sort of continuous parameters defined in terms of a very small set of continuous parameters. Discrete means they are A1, it's a separate matrix, each of them is a separate matrix. In the present case, let's look at whether Lorenz group transforms as is actually a continuous group. Why? Because let's take this this aspect about boost, meaning boost, or the rapidities, or the boost. So let's take a boost in the x direction. The x direction boost are given by this set of Lorenz transformations. So there, okay. Now these boosts, they have, as we said, they should have an inverse, they should have an identity, they should have an associativity. So they have closure. Okay. So first of all, these boosts are continuous parameter there. Say for example, let's just take boost in the x direction. The boost in the x direction are defined by one set of parameters, which is xi. So as xi take different values, we will have different Lorenz transformations. Okay. As xi, the rapidity changes, so you have different set of parameters, and this group has infinite number of elements. There are infinite number of Lorenz transformations possible as xi takes values. Okay. As xi takes different values, you can have infinite number of Lorenz transformations. Now all of them belong to one set, which is the Lorenz transformation set. Okay. And then you can check that it satisfies closure, it satisfies associativity, it satisfies identity, it satisfies inverse. All this it satisfies. Okay. But this is not true in a general, so they don't really completely form a group in, this is not, say for example, if you add boosts in different directions, they don't really form a group. Okay. So for that, you need one more element, which is called rotations. Okay. So like I said, you will have 3 boosts in each direction. Rotations. Okay. So you would need rotations. So if you want to add boost in different directions, you would need rotations. So rotations, you know what they are. So you will just need rotations in space direction. So you will have x, y, and z, and you will have possibly x prime, y prime, z prime. So the rotations of frame. So this is O1, this is O2. So you have transformations, okay, between these two, which are just ordinary space rotations. Okay. So only if you put together rotations also, okay, the Lorenz transformations form a group. Okay. So rotations are also a part of Lorenz transformations. So these transformations which we have, okay, so this means that there are 3 rotations. How are rotations defined? Say for example, t, x, y, z is given by the Euler angles. You can define it in terms of the Euler angles in 3 dimensions. So you will have a transformations in this particular fashion. So 1, 0, 0, 0, 0, 0, 0. Then there is this block matrix, which I call it as rotation matrix R, and then there is this t, x, y and z, where R is a matrix made up of the Euler angles which define, which you have studied in your classical mechanics course, which defines rotations in different directions. So, theta, psi, delta, say for example, phi. So, R is this one, where r of theta you can define it in x y rotations, cos theta, sin theta 0, minus sin theta, cos theta 0, 0, 0, 1, and r of psi would be, say, let us say it in x y x z directions, 0, sin theta 0, 1, 0, minus sin theta 0, cos theta, and then r phi would be 1, 0, 0, 0, cos phi, sin phi, minus sin phi, cos phi. So, what we have seen is that, so there are 3 rotation angles, these are the 3 parameters. Rotations, and then there are 3 parameters for the boost. So, these are these 3 parameters, say for example, in boost in xt direction, okay, 3 parameters for boost, okay, sorry, 3 parameters for boosts. So, you can have boost which are given in x and t direction, or t and x direction, say for example. How did I, one second, let me just see how did I write it, x and t. Given by cos h xi, sin xi, sin xi, cos h xi. Then you can have yt direction, okay. You can write in cos, instead of xi you can have not beta, gamma is not xi, let me call it a xi 1, xi x, xi x, xi x, xi. Then you can have xi y, sin xi y, sin h xi y, cos h xi y. Then you have zt, also give me something like this, cos h xi z, sin h xi z, minus sin h xi z, cos h xi z. So, you will have 3 parameters for the boost. So, 3 parameters for the boost. So, now let us come to the counting of the parameters. How many parameters? All these parameters form the group. So, you have x mu prime is equal to lambda mu nu prime x nu. This lambda mu nu is a matrix 4 by 4 symmetric matrix. So, how many elements it is made up of? 4 4s are 16. So, for example, let us count them. So, if you have A11, A12, A13, A14, A12 is nothing but A22, A22, A23, A24, then A33, A34, then A44. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 parameters. You can count it in a different way. Actually, you can just use the formula for n into it's essentially n into n minus 1 by 2. Okay, and then there is the orthogonality condition, which are lambda mu rho, then mu delta is equal to delta rho delta. Orthogonality condition. So these are 10 parameters. These are 4 conditions. So 10 minus 1, total free parameters for any Lorenz transformations would be 10 minus 4, that is 6 parameters. And what are these 6 parameters? These are 3 boosts, which we have seen zx, zy, zz, z, and 3 rotations, rx, okay, theta psi phi, theta psi phi. So all of them, the complete set including boost and rotations, the set of all, it's a continuous set. Boosts plus rotations, this set forms a group. That means it satisfies the thing which I mentioned earlier, and this name has a name which is called SO31. The group has a name which is called special orthogonal group of 4 dimensions 3, 1. Why does it have 3, 1? Because it doesn't leave. Say for example, the same group, if you don't have time, say for example, if you have x1, x2, if you have 4 dimensional fields, this gives me SO4, because here metric has a minus sign. So to distinguish that compared to SO4, so SO4 will leave x1 square plus x2 square plus x3 square plus x4 square, this length of a vector invariant, whereas SO31 will leave the invariance x0 square minus x1 square plus minus x2 square minus x3 square. It will leave this one invariant. So SO31 will leave this metric signature invariant, or the way we are considering, this is minus x0 square plus x1 square plus x2 square. So to distinguish, because of this minus sign, so to distinguish the length of the vector which is invariant, we call this group as SO31, whereas for a normal rotational groups, or for many of this normal rotational group, that group is SO4. Say for example, if you have 4 dimensions and all the 4 are like normal vectors, so x, y, z and some z prime or something, okay, this will leave this gives a group called SO4. So this is about Lorenz transformations. So to summarize, the Lorenz transformations we have seen, they consist of 3 rotations and 3 boosts, okay, and they leave this line element which we had introduced in the part 1 as invariant. Now we need to introduce something else, essentially some more quantities, okay. Let me stop here and then continue with the other set of quantities.